Hello?
Yes, we hear you loud and clear. Great. So right before we get started, I introduce Nabi, our speaker. I wanted to welcome you guys to the final session. We will be doing another Q&A at the very end. Please feel free to submit your questions in the text box there in the GoToWebinar console, excuse me. And we will be addressing your questions anonymously. We'll be sending completion certificates by email next week. And if you experience any technical difficulties, please email our team at webinar@origin-and-cause.com. I'd like to introduce our speaker, Nabi Gudarzi. He is a professional engineer in Ontario, Alberta, and Atlantic Canada. He has over 10 years of professional practice experience and investigates and provides repair schemes for damaged and under-designed structures and conducts structural investigations on industrial and commercial buildings. So I'll pass off the screen and the mic to Nabi.
Thank you, George. So do you see my screen?
Yes.
Yes, okay. Thank you, George, and thank you, everyone. So in this presentation, I want to present 3 case studies. Case study 1 is roof collapse of a wood-framed workshop. And then I'll go through some examples of stiffness, bending, and buckling, and talk about the fundamentals of these 3 concepts in structural engineering. And in case number 2, we'll talk about roof collapse of a steel-framed farm building. And then we'll give examples of bracing and buckling failure in steel buildings. And case number 3, roof collapse of a steel-framed commercial building. Okay, so case study number 1. Okay, so roof collapse of a workshop under snow. So it was a mixed-use building. The areas included storage, workshop, and lean-to garage. So this is the main area of the. So this is the main area of the workshop, and there was a lean-to garage here. It was built in 1980, and it was wood-framed building with gable roof. And there were rafters over the lean-to buildings. So here we have a lean-to garage, and there was another lean-to storage area here. And the roof of these areas were framed by rafters, and there were wood trusses over the workshop. So the roof of the main building, the main workshop, was framed with wood trusses. So the notice of loss was the roof collapsed under snow at the end of February, where the snow is also wet. Our assignment was to determine cause of roof collapse. Here you can see the view of the collapsed garage, the lean-to garage, the one with the rafters. And here you can see the general view of the roof. Of the garage. So we started investigating. We attended the scene, took a look at the roof trusses over the garage, and also the lean-to garage, and also the trusses over the workshop and the rafters over the lean-to garage. The roof of the lean-to garage was framed with 2x10 rafters at 4 feet, and the roof of the workshop, the trusses, we didn't see any lateral bracing between the trusses. Usually between the trusses there should be continuous horizontal bracing, complete with diagonal bracing. But we didn't see, as you see here, there is none here. Now, in this example, I want to particularly talk about the collapse of the roof trusses. For the lean-to garage, the rafters were not designed properly and they were widely spaced. So, but there are a couple of points I want to talk about the collapse of the roof trusses. So we did some code review to see why the roof collapsed. Maximum ground snow on the date of loss was 50 centimeters. Maximum wind gust on date of loss was 55 kilometers per hour. And this was a farm building, so we looked into Canadian Farm Building Code in 1975. The design ground snow load was 3 kPa, which is equivalent to design ground snow depth of 86 centimeters. This means that if the building was built to satisfy the requirements of the code at the time it was built, it should have carried up to 86 centimeters of snow without collapsing. But it collapsed under 50 centimeters of ground snow load. There's another thing I should mention here. When we say ground snow load of 50 centimeters, the amount of snow on the roof is different than the ground snow load. There's a formula to convert ground snow load to the roof snow load. But regardless, those formulas are similar when we do the actual ground snow load to roof snow load, or when we go from design ground snow load to roof snow load. So anyhow, if it was designed properly, it should have resisted the snow on the date of loss. Design wind gust was 77 kilometers per hour. So again, if it was designed properly, it should have resisted 77 kilometers per hour. But on the date of loss, the wind gust was 55 kilometers per hour. So right now, at this point, we can rule out ground snow or snow load or wind gust. So these two are not the culprits. So let's see what is the culprit then. So as I mentioned, there was no bracing between the trusses. So here in this image, I'm showing a section of roof trusses. You can see, so the trusses are oriented and coming out of the page. So and the trusses are at 2 feet spaced. At the top, you have the top cord. At the bottom, you have the bottom cord. And between the top cord and bottom cord, you have the webs. On top of the roof, on top of the trusses, you had strapping and metal sheets. And over that, you have, when it's snowing, you have snow load. And at the bottom, of course, you have, at the ends of the trusses, you have the top plates of the wall. So here I'm showing the double top plates of the wall. Now, here's the thing. If everything is perfect, I mean, if the snow load is exactly uniform, and if the material of the trusses are exactly homogeneous, and if all the trusses are exactly vertical, then no collapse, no buckling or no collapse would happen. But this is almost never the case. So you have some irregularities in structures, in every structure. Here there might be some more snow, here a bit less snow. The trusses might be, they might have a bit out of plumbness. Plus the material itself might not be, very likely it's not homogeneous. Because of all these irregularities, it is very likely that you get a small rotation of the trusses under vertical load. Now I'm gonna talk about here. So you have a small rotation. You have D1 displacement at the top, and you have the vertical load at the top of the truss. Now, because of this D1, this P force P times D1, it gives you a moment. We call it a moment. P times D, it gives you a moment at the about the bottom of the truss. Now, there's nothing at the bottom to resist this moment. So this moment caused the truss to rotate even more. So now you have D2, which is larger than D1. So this PD then will become PD2, P times D2, which gives you a larger moment, and the larger moment will rotate the truss even more. So you can see that it's very progressive. You started from a small D1, and now because of that, it's getting larger and larger to the point of collapse. So this is called instability. And it's a sudden mode of failure, and it is catastrophic. Now, here's how it can be prevented. If there was horizontal bracing and diagonal bracing, the collapse could have been prevented. So, and these bracing are they take a small portion of the cost of construction, but they play a very important role. So let's see how it works. Let's say this truss, it wants to rotate. It pulls on the diagonal brace, and the diagonal brace is restrained at the bottom. So, so the force, this tension force, and this lateral force is taken by this brace to a support. So this is for this truss. Now this truss, if it wants to rotate, it creates a tension force here in the horizontal brace. Now, and from the horizontal brace, this tension force, it will go to the diagonal brace, and from the diagonal brace, it goes to the bottom of the truss, which is a good support for the brace. So this is how the braces work. So you need both horizontal brace and diagonal brace. Now, if you didn't have the horizontal brace, sure, this diagonal brace could prevent this truss and this truss from buckling or from collapsing, but this truss could collapse because it would not be connected to anything. So you need a horizontal brace, and they call it collectors, to collect all the forces of other trusses and take it to the diagonal brace from where the force can go to a support. Now, here is an illustration by the Building Component Safety Institute of Canada. It gives you a guidance on the bracing of roof trusses. You can see that there should be continuous lateral bracing, and it should be lapped over 2 trusses or continuous lateral splice reinforcement. And as I said, there should also be diagonal braces as well. And the diagonal braces should be spaced at 20 feet maximum. Here's an elevation or section of the truss. As you can see, the bottom chord, top chord. Here you can see the continuous lateral bracing. It should be lapped 1 truss space, and you should have diagonal braces, and they are connected to the blocking at the top and bottom, unless otherwise specified by the designer. Okay, so the possible cause of loss we determined to be lack of lateral bracing. Now, if the roof was inspected before, the owner could have installed lateral bracing, and that would have prevented this collapse. So this is how it could have been prevented. Now, before I go to the second example, I want to mention a couple of concepts in structural engineering. I want to talk about stiffness here. Stiffness is the difficulty to deform an object. So the harder it is to deform an object, that object is stiffer. For example, we say axial stiffness of a straw is greater than its lateral stiffness. It means it's stiffer in the axial direction. So here I'm holding a straw, and if I put a lateral force at the top, I can easily deform it by, let's say, 2 inches. I'm going to talk about these other forces later. Now, about the straw, if I hold it at the bottom and this time I try to pull on it, I cannot pull it by 2 inches. So we call it's very stiff in the axial direction and very flexible in the lateral direction, or in the flexural direction. Lateral stiffness of a ruler along its width is larger than its lateral stiffness along its thickness. So again, I can easily, here I hold the bottom of the ruler and I can easily push the top of the ruler by, let's say, 2 inches. But here, if I hold it the other way, I cannot easily bend it like that. So in bending, one side is in tension, the other side is in compression. So imagine if when you are doing a side stretch, one side of your body is in tension, the other side is in compression. Similarly, let's say you have a column. When it's under lateral load, it can be a wind or earthquake. When it bends, one side is under compression, one side is under tension. And this, the bottom should be fixed to resist that bending moment. And this is how we show fixed support in structural engineering. Now, if the bottom is not fixed, the column can easily tip over. So it should be either fixed at the bottom or it should have adequate bracing. The flexural stiffness depends on cross-section of the member, length, and material. For example, let's talk about the ruler. The ruler, the cross-section is just a rectangle, okay, the thickness and the width. Not only the cross-section is important, but also the orientation of the cross-section with respect to the orientation of the force is important. So the same ruler, if the width is along the force, it shows a very stiff behavior in bending. But if the thickness is along the force, it is very flexible. So not only the shape of the cross-section is important, but the orientation of the cross-section with respect to the lateral force is also important. Length of the member is also important in flexural stiffness. Here I'm holding the bottom of the ruler. If I were to hold the mid height of the ruler, I would have to push twice as hard to bend it by 2 inches. Material is important, of course. If it was a steel ruler, it'd be stiffer. Now buckling. So axial buckling depends on slenderness of column. And I'm going to talk about that. Now, here I'm showing a column, and there's a compressive force at the top. If everything is perfect, I mean, if the column or the ruler here is exactly homogeneous, and if it's exactly straight, and if the force is exactly applied at the centroid of the cross section, you will not have any buckling. But it never happens. There is some non-homogeneity. So by that I mean the properties of the material in a ruler or in any object from one point to the other can be different by a little bit, but still it can be different. Okay. The other thing, the ruler might not be exactly straight. It might be bendy a bit. The force might not be exactly at the centroid of the cross section, and also for a column, there can be some vibrations or some wind. So there are some lateral forces that make the column to bend. Now, so when it bends, then it is susceptible to buckling, and I'm going to talk about that. So now it bends and it's going to buckle. The buckling depends on the cross section of the column. So when it wants to buckle, it buckles about the weak axis. It buckles about the thickness, and also it depends on the length. The longer an object is, it is easier to make it buckle. Okay. Support conditions. So here I'm showing a hinge, which it means that the tip can rotate about this support. If it was fixed, it'd be harder to buckle the ruler. And also material. So the stiffer the material, the harder it is to buckle. So all in all, for a material that is very easy to buckle, we call it it's slender. Okay, so all these define slenderness. So longer column is more slender. Okay, or bigger cross section is, we call it make the column very stocky. Okay, so the slenderness of a material, a column, determines its buckling capacity. For example, here we say a ruler has high slenderness about weak axis. It means it's easy to buckle about its weak axis. Okay, and it's very hard to make it buckle about its strong axis, which is along its width. The longer a column is, the more slender it is, and more slender, as I said, it's easier to buckle, and slenderness depends on these factors. Now, let's talk about buckling mechanism. Compressive buckling is due to combination of axial force and progressive deflection. As I said, under compressive force, let's say there is some very small deflection in the midspan of the ruler. So here you have a small d. Okay. Now this P times d. Okay, so here you have a pin. This P times this d creates a bending moment here at the middle of the mid height of the column. Now at this point, if the column does not have enough flexural stiffness, this d keeps increasing. Okay, and this bending moment keeps increasing to the point that it breaks. Okay, but if the column has enough flexural stiffness, this deflection increases by a little bit, but at some point it stops. Okay, so buckling depends on the stiffness of the material. Okay, now having said all these, stiffness, bending, and buckling, and of course the bracing, let's talk about case study number 2, which is roof collapse of a steel framed farm building. So this was a steel shelter built in 1960s. It was a 3-hinge portal frame on strip footing. So a portal frame, it has like a pitched roof and columns. There are 3 hinges, 1 at the top and 2 at the bottom. Okay, when I say hinge, it means it can easily rotate. The cladding of the building was sheet metal panels on the roof and walls. You can see the general view of the building. Of course, the collapsed shape. So this is the general view of the roof. You can see the roof steel trusses, and here you can see the vertical trusses. Again, a part of the roof truss, and also these rods, you can see that they are bracing the bottom cord of the roof truss. Another view of the roof structure, and also the collapsed shape of the trusses. So the notice of loss was that the roof collapsed under snow, and our assignment was to determine cause of loss. So we started our investigation, looked at the failure pattern or failure shape of the roof. You can see, first of all, this is the middle of the roof. You can see this is a hinge. I'm gonna zoom in here so you can see this is a bolt. It makes it a hinge at the top. That's why we call it 3-hinge portal frame. And you can see these 2 trusses at the bottom, they have buckled in the same direction. So the bottom cord has kicked out to the right. And here again, another view of the connection of the roof truss and the vertical truss and the bracing. You can see again the buckling of the cord. Again here, this is the hinge. This is the bottom cord. We reviewed the weather information. Again, we saw that maximum ground snow on the date of loss was 54 centimeters, and maximum wind gust was 58 kilometers per hour. So similarly, it was, so these values were below the design values, meaning if the building was designed to the building code of the time it was built, it could have resisted the loads. Having said that, at that time, 1960s, there was no building code in that jurisdiction to govern the construction of building. There was a National Building Code of Canada, but it was just a model code. It was not reinforced in that jurisdiction. So here another view of the collapsed roof. You can see again the trusses, the bottom cord has kicked out in the same direction. I'm going to talk about that, why it has happened. All we saw was horizontal rods as supposedly to brace the bottom cords. A closer view of the bottom cords of the trusses that have buckled. Again, another view of that. Another view of the buckling of the bottom cords. Now, possible cause of loss, lack of adequate bracing. And the reason here is that we only had horizontal bracing. If you remember from my first example, horizontal bracing alone is not enough, because as you see, all the bottom cords, they buckled in the same direction, and there was no diagonal bracing anywhere to prevent it from buckling. And why did the bottom cords buckle because the bottom chords are under compression. Around the ends of the beam, always the bottom chords are under compression. Now here, I'm going to show you some examples of bracing in steel buildings. So here is a metal building. I'm going to zoom in to show you the bracing here. First of all, this bracing, this cross bracing, this is tensioned steel rod bracing. This is to provide lateral stability to the building. And you can see how small it is in cross section. These are just rods and holding this building together. So you can see that bracing constitutes a very small portion of the construction cost and material, but it's very important. You can have a very well designed building with large size beams and columns, but without bracing, without adequate bracing, and without adequate detailing of the braces, it can collapse under just regular loading and regular wind or regular snow. So we call it the devil is in the details. Yeah, so here it's showing the diagonal bracing of the bottom chord. Now here in this particular example, there is no horizontal bracing between the bottom chords. It is okay as long as you have diagonal bracing connected to all bottom chords, which in this case they have diagonal bracing. So this is one example of how it should have been braced. Our example, it should have been braced like it should have had like at least one diagonal braces at some spacing to prevent it from buckling. Another example of a metal building. Now this collapsed, part of the building collapsed because of some lack of temporary bracing, but here what I'm going to show you is, I'm going to talk about that. First of all, you can see again cross bracing to hold the building together and prevent instability. And also diagonal bracing between the bottom chords of the beams to the joists. Now again, like I said before, under bending, one side is in tension, one side is in compression. So for the beam, around the end of the beam, you have a bending moment. And because of that bending moment, the top chord or the top flange is in tension and the bottom flange is in compression. And every time you have compression, you have likelihood of buckling, and you have to check that. So to prevent that buckling to happen, they installed the diagonal bracing. Another example of better focus. Yeah. So here, so you have a beam here. So you have a beam, you have a bending moment here. Here is under tension, and at the bottom it's under compression. So this compression makes this compression here makes the web to buckle. And to prevent that buckling, all they had to do was put a plate here. We call it stiffener. This is a stiffener. This is an example of stiffener. So they should have installed a stiffener between the bottom chord of the beam and the other, or the bottom flange of the beam. So here, between here. Okay. Now, here I'm showing in this building the diagonal bracing of the bottom chord of the beam, and yet it has buckled. I want to make a point here. The braces, whenever you brace something, it has to it has to have enough stiffness. Buckling depends on stiffness. I explained in the case of a column under buckling that how it depends on the flexural stiffness. So here, yes, it has braces, but so the brace takes the compression, okay? So when it takes the compression, it brings the compression force should bring it to a reliable support, but it brings it to a joist, which is fine as long as the joists were designed for that. Okay, but here the joist could easily bend, and when they can bend, it means the stiffness of this brace is now compromised because of the bending of the steel joists. So the bottom cord could easily buckle because the braces were not effective. Now, case study number 3. It was collapse of the steel structure of a commercial building. So it was a commercial building of structural steel construction. If a part of it was under construction, the first phase of it was fully constructed. And this is the original building, general view of the building. So notice of loss was that the roof suddenly collapsed. So sudden collapse of the roof. And our assignment was, like always, to determine cause of roof collapse. So we took a look at the collapsed members. So here you can see the bridging between the steel joists, and this is the roof girder. 25% of steel was erected prior to the date of loss, and the open web steel joists were not welded to the girder, and uplift bridging at end panels were not installed, and also temporary bracing between the columns were not installed. So essentially what you have is similar to our first example. So you had a group of columns. There was no temporary bracing between the columns, and you had the steel joists from above. And in this case, you remember I said if you get a small deflection because of the P times D, it creates bending moment, and it eventually makes the roof to collapse. Here, you also had the effect of the wind. So this is a worst case scenario. So not only you have the risk of instability because of irregularity of loading and irregularity of material properties or out of plumbness of the columns, but also you had wind. And this wind alone could create enough deflection to produce enough bending moment for the column to buckle, or for the column to collapse. And of course, the bottom support of the column were not designed for bending moment. These industrial buildings are usually braced with cross bracings, usually steel rod bracing. So the bottom of the columns are usually pinned or hinged. We did some code review, and it's important to note that it is installer's responsibility to install temporary bracing, and there was no temporary bracing installed in this building. This is according to the CISC Code of Standard Practice, and as per AISC Design Guide number 10, wind speed for temporary bracing can be reduced by 20%. So for temporary construction, when you put temporary bracing, you don't have to design the temporary bracing for the full design load of the code. You can reduce that by 20%. which is understandable because what are the odds that you get a 50-year, you get the highest wind in 50 years during that construction period? It's very low probability. So it allows you to reduce the design wind speed by 20%. So if the temporary bracing was installed, it would not have collapsed. So adequate bracing was not in place. So this is our investigation results. Adequate bracing was not in place. Damage would still have occurred even if adequate bracing was in place. On the date of loss, the wind was really high, and it could have resulted in some, let's say, deformations and stuff, but it would not have made the building collapse like this if the temporary bracing was in place. So again, installing temporary bracing is imperative during construction. Buckling failure can be sudden and catastrophic. Bracing constitutes a small portion of the construction cost, but plays a significant role in preventing structural failure. And we say devil is in the details. So it is very important to pay attention to bracing and its details to prevent catastrophic and costly collapse. Thank you very much for your attention, and I'm glad to address any questions. Thanks.
Thank you, Nabi.
Yeah.
So I'm just gonna put your information here on the screen while we answer any questions that come in. Folks, you can submit your questions in the question tab. We have two submitted questions. One is, regarding the snow load, how far back can you go to hold the builder responsible? In the example, the 1975 code was referenced. If a building was built in 74, collapses today, can you go after that builder? I imagine that that's more of a subrogation expert's question, but Nabi, from a technical standpoint, do you have any thoughts on this?
So what I know, the designer is responsible for 10 years for the building. For the builder, I don't know right now. But I know that, like, in design, if your design is faulty, you can be sued for if failure occurs before 10 years after the construction.
Cool. Yes, I see here someone had just typed in Limitations Act is 10 years prescription from my understanding as well. So very interesting. That's a great question.
Yeah.
Like, I mean, if they're in business and you can find them and all of that, you know, what would be restricting? And I guess there is a limitation to that.
Now,
Yeah, George. Oh, sorry. If I could chime in real quick, I think the question is also asking if the building code is retroactive, because we're talking about a building built in 1974 and asking if the code from 1975 applies to it.
So, well, definitely not. So we always check with the building code of the time the building was built. Okay, so of course, like if the building was built in 1980s and we cannot check it under current code, like for sure we have to go back and check code of 1980 or any code that was in effect at that time. Did I answer the question?
Yes.
Okay.
Okay, next question. Is it fair to say that that lack of or improper bracing is a common cause of failure?
We've seen a couple of files that they collapse because of that, usually roof trusses. And if it's sudden and catastrophic, it is very likely that it's lack of bracing. But I wouldn't go as far as saying the common cause, because there can be other issues. Like I've seen under-designed members, like under-designed rafters and stuff. Of course, we don't have buckling problems in rafters. But for trusses, the other possibility I've seen a couple of times is inadequate connections. So the mending plates do not cover enough of the web and cord members. So that's another kind of cause that we've seen many times in our files. Yeah.
Great.
Yeah.
Thank you. Next question. In an older building, is it possible to determine if the building was under-designed or poorly built?
It is very hard to determine that, because for design, you need to have the design drawings. And in old buildings, you almost never have the drawings, unless it's well, for commercial buildings, it's very likely to have the drawings. And but for definitely residentials, it's very hard to, I mean, they don't exist. But for commercial buildings, you can determine that. You can compare the design to what was constructed. Because a lot of times we've seen that when a building goes to construction, the builder deviates from the design drawings for different reasons. And yes, so you can determine that.
Cool. Very cool. And last question. Are the requirements different in terms of bracing for steel and wood frame buildings?
Well, the concept is the same, but of course the requirements are different, because wood and steel are way two different materials with different material properties. So, like, but the concept for sure is the same. Yeah. But the exact requirement is not the same. Like, you don't say in steel buildings the bracing should be at 20 feet. No, you don't say that. Like, in steel buildings, you need to design the bracing and put it where it should be. But the concepts for sure is the same. Like, when you have compressive force, you need to check for you need to check for buckling and instability.
Yes. Cool. Great. Well, thank you so much, Nabi, and thank you all for joining us today. It's been a great day, full of great questions. Thank you all for joining us. We will